All right, hello and good Monday afternoon. Um, uh, let's see. This is our last week in September, if I'm not mistaken. Yep. And then we're into October, which is awesome. Definitely looking forward to a little more fall weather. Um, Hey, well, I almost said good morning, good afternoon to everybody up on the live chat. I've got a couple things by way of announcements today. Oh, hang on. There we go. Okay, so a couple things by way of. Whoops, nope. Let's go up here. Uh, Whoa, holy moly! Sorry, hang on. I don't know. Oh, I know. I'm like, I don't know why my pen was super fine. I think I was using this to sign things over the weekend. So a couple things by way of announcements. The first, has to do with our lecture pace. So we're a little bit behind schedule, and to get us back on track, I'm going to shift things around a bit. Normally, the way Folsom Lake College handles Chapter 5, which is the gas laws, is it cover the normal way sorry, okay, wait, hang on. Restart English. Normally, when we're meeting in person, Folsom Lake College covers Chapter 5 in 2 lab lectures, not in the main lecture section. And we're a little bit behind in our lab schedule. To get us back on track, I'm going to be moving the Chapter 5 lectures to the lab portion of the course. So we're going to conclude Chapter 4 probably next week. But Chapter 5, I'm going to cover in 2 lab lectures. So these will be airing at the beginning of the lab portion of the course, so the 7 to 10 situation, on YouTube, and they're going to be part 1 is going to be on this Wednesday, 9:30, and then part 2 will be on a week from today, which is 10/5. All right, so in October. Both of these will be airing at 7 p.m. On our YouTube channel, so right here. Even if you're not in my lab section, this is where you'll need to tune in to see the lectures for Chapter 5, and that material will be tested in the lecture portion of the course. So that is where we're going to be handling Chapter 5. Now, something that's important to note, Chapter 5 will not be on Exam 2. All right, so Chapter 5 is not on Exam 2. Exam 2 will cover Chapter 4. Or I should say, up until Chapter 4. Or I should say, everything through Chapter 4. That's the way to say it. I don't have anything else to say about the second exam right now, but I did want to say that even though we're going to start lecturing on Chapter 5, that material won't show up on exams until the third one. Okay, so that's one thing. The second bit of announcements that I wanted to talk about are the oops, nope. Let's open a new slide. The exam review packets. These are almost done. They'll be posted later today. The prereq exam review packet. It wasn't that complex actually. Once I broke down the analysis, it's fairly straightforward. The exam one, it actually most of the problems were kind of focused on a couple concepts, and again, you can see I talk a little bit about it in each review packet. That being said, the one thing that I wanted to talk to you about is for the prereq review packet. This is just for review. There are no points associated with There are no points associated with the completion of this one, but for the exam one review packet, I'm writing kind of like a problem set, a problem worksheet to do, and for this one, there will be 5 points of extra credit for the completion of this packet, which is 7% of the exam total. So completing this and turning it in will essentially give your exam score a 7% boost if you complete it fully and correctly and perfectly. A couple things about doing this assignment. So it's going to be a handwritten thing. I'll create a portal for you to submit it to in Canvas. And for this, answers are not enough. You must show your work. And these instructions are included with the packet. You must show your work. It's got to be perfect as well. Not just the answer, but in the work shown, in the algebraic steps shown. It's out of 5 for each. Okay, so show your work, no errors, and it must be clearly legible. If I can't read your work, then it's the same as not showing me your work, because you haven't showed me your work. So, and again, there's more detailed instructions, but this is kind of the gist of it. You can get a 7% bump if you do this thing. It's going to be about, I haven't quite finished it yet, but like 8 or 9 problems. They're all going to be problems similar to the ones that the class as a whole was struggling with. So the point is review, but also the point is to kind of incentivize review, to give you guys some help by doing this extra work and helping get ready for the stuff coming in the future. Let's see. Okay, we got a couple questions. Leanna, great question. Exam 2 is just going to focus on our lecture material. Sometimes the lecture and lab material cover similar things, so I don't want to say like nothing you'll see in lab will show up on lecture, but when you're studying for the exam, you just want to focus on what we're covering in the lecture course, because that is what I'm basing the problems on, and that's what I'll be testing on. The explicit lab content is tested for in the lab quizzes. All right, so anyways, you'll see this will be, I'll post an announcement when these are up. I finished writing the prereq exam packet. I'm still working on the exam one. Both of these will get posted by the end of today. And if you're dissatisfied with your exam 1 score, this is a way to give yourself a 7% bump, whatever score you got. Okay. So with that being said, let's go ahead and dive in to our new topic. We're continuing in chapter 4, and on Wednesday we finished precipitation reactions. All right, and I said that we have two more reaction types left in chapter 4. Acid-base reactions and redox reactions. And the order in which they're treated in the book is the book hits acid-base first, redox second. I'm going to flip those, all right? So if you're one of those humans who likes reading along in the book, jump to the redox portion, and then we'll backtrack to the acid-base portion. The reason why I'm doing this is I find that usually students struggle more with the redox portion of the course, and so I want to give you guys as much time to study the redox stuff as possible before you encounter it in the wild on an exam. So with that, let's talk about redox reactions. All right, redox reactions. Redox stands for reduction, oxidation. Oops. Actually, hang on. I need to open this, or I need to write this in a new slide. So redox stands for reduction oxidation reactions. All right, and so a good place to start here might be knowing what reduction and oxidation mean. Now, reduction happens when an element loses electrons. All right, when you lose electrons, that is reduction. No, sorry, dyslexia makes life a little more exciting. Reduction happens when an element, gains electrons. Gains electrons. Oxidation happens when an element loses electrons. All right, so you lose electrons, oxidation, you gain electrons, reduction. This is where there's a bunch of different acronyms for this. Use whichever one you know, whichever one you were raised with. The one that I grew up with was an acronym that goes like this. Leo says GER. All right, and the Leo stands for lose electrons, oxidation, and the GER is gain electrons, reduction. All right, so Leo says GER is one way. There's other ones. I know oil rig is a popular one, etc. So those are the definitions for reduction and oxidation. Now, a redox reaction is a reaction in which reduction and oxidation occur. All right, so it's literally talking about when we talk about redox reactions, we're literally talking about reactions that involve the exchange of electrons. All right, it's an electron exchange. Now, let's look at a redox reaction. Let's see what do these things look like. Here's an example. Oops. Here's an example of a redox reaction. 2 molecules of hydrogen gas reacting with 1 molecule of oxygen gas to produce 2 molecules of water vapor. All right, that is a redox reaction. And you may be going, well, wait a minute. Where are the electrons, right? You said that redox reactions are reactions that involve the exchange of electrons. Where are they? I don't see any electrons in this reaction, all right? Now, there's a reason why that's the case, all right? It's because electrons, redox reactions, electron exchanges are basically drug deals, all right? Someone's showing up and they're selling, someone else is showing up and they're buying, but you don't actually see the electrons exchange hands, right? It just looks like people are eating chicken at Pollos Hermanos, right? It just looks like people having lunch, but there's a buyer, there's a seller, and electrons are exchanged nonetheless. Your job for this portion of the course is you need to narc on the buyer and the seller. You need to figure out who is giving the electrons, who is receiving the electrons, and the way you do that is by assigning something called oxidation numbers. Often they're called oxidation states, and we'll get into how to do this in a minute, but an oxidation state is basically a number that gives you an idea, that tells you how much charge an element has in a specific molecule, ion, whatever. So I'm going to write in the oxidation numbers for all of the elements on both sides of this reaction. So here we go. Hydrogen in H2 has an oxidation number of 0. Oxygen in O2 has an oxidation number of 0. Hydrogen in H2O has an oxidation number of +1. And oxygen in H2O has an oxidation number of 2. All right? Now let's assess how our charges change moving from the reactant side to the product side. Let's look at oxygen. All right? Oxygen starts at 0 and ends at -2. If you're starting right at 0 and ending at -2, you've gained electrons over the course of this reaction, right? Electrons are negative particles, so if you start neutral and then negative, you've picked up electrons along the way. So oxygen, we would say that oxygen has gained electrons. All right, oxygen has gained electrons, therefore, lose electrons oxidation, gain electrons reduction, GER, right? We say that oxygen is reduced. All right, let's look at hydrogen. Hydrogen starts at 0 and ends at +1, right? Hydrogen starts at 0, ends at +1. That means, so let's think about it. Hydrogen, if it starts neutral and ends at +1, it's gotten positive, so it must have lost negative particles, right? Hydrogen has lost electrons, which means that hydrogen is oxidized, all right? So oxidation numbers or oxidation states allow you to look at a reaction and figure out who's really losing electrons, who's really selling electrons, what that flow, where that flow is, and in what direction it's going. To be able to determine what's reduced and determine what's oxidized, you first need to be able to assign oxidation states, and that is what we're going to invest our time in learning right now. We're going to start by learning to assign oxidation states, and then we'll continue our discussion of redox reactions. All right. So let's dive in. Something I want to say before I get going with this part first. I call these oxidation states. Depending, your book calls them oxidation numbers. They're the same thing. Different names for the same thing. The second thing that I want to say is the method that I'm about to teach you is a little different than the method set up in the book. Mine is a little simpler. Okay, mine will actually is 4 rules. The book has something like 7, and you have to memorize exceptions and stuff. They both get you to the same place. Here, Bailey, hang on 1 second. So if you already learned how to do this the way the book teaches, and you don't want to learn my way, you're totally good. If you've never learned how to do it before, I think my way is simpler, but take a look at the books. They both work. But that being said, I didn't want anyone to be confused if they watch this lecture, look at the book, and they're like, wait, it's different oxidation rules. They totally get you to the same place. So use the one that's easiest for you to remember. Bailey, that is an excellent question. And yes, the answer is yes. It totally is. We're going to circle back and talk about how to determine the oxidizing agent and reducing agent after we learn how to assign oxidation numbers. So I'm not skipping that part. We'll totally cover it in all of its glorious detail. But first, we should learn how to assign oxidation states. All right. Now, the first rule of assigning, so something else you should know, these are in hierarchy. So you always use rule number 1 if you can. If it's not enough by itself, you move to number 2, then to 3, then to 4 is your last resort. But you're trying to use as few of these as possible, and you always start at the top. All right. So the first rule for assigning oxidation states is the oxidation state of all elements. The oxidation state or states, of all elements must add to the total charge. All right, so let's do some examples using rule number 1. Determine the oxidation state of sodium. Sodium metal has no charge, therefore its oxidation state is 0. All right, what about the charge for sodium metal? All right, sodium metal has a charge of +1, therefore the charge on sodium, the oxidation state on sodium is +1. All right, what about the oxidation state for oxygen gas? Well, oxygen has no oxidation state, therefore the oxidation state of each oxygen atom inside that molecule is 0. Whoops, didn't mean to write that in orange. What about oxide? All right, oxide is an anion that has a total charge of -2. So the oxidation state of oxygen in a molecule of oxide is -2. Now, what about the oxidation state of peroxide? All right, check this out. Rule number 1 says that the oxidation state of all elements present must add to their total charge. That means that that 2 times the oxidation state on oxygen is equal to our total charge, which is -2. To find the oxidation state then of one oxygen atom, we got to divide both sides by 2. And we find that the oxidation state of oxygen here is -1. All right, so those are some examples of how you would use the first rule to assign oxidation states when there's only one type of element present in your molecule. All right, that's rarely the case though, so we're going to need a couple more rules if we're going to be able to determine oxidation states in general. Second rule is, and again, you only use the second rule if the first one can help you. Hydrogen is always +1 unless it is the only nonmetal. Unless it is the only nonmetal. Then it is -1. All right, so hydrogen in a compound will always be +1 unless it's the only nonmetal, then it'll be -1. Let's do a few examples. So let's determine hydrogen's oxidation state in water. All right, rule number 2, hydrogen's always +1 unless it's the only nonmetal. So the question is oxygen a metal or a nonmetal? You look at the periodic table, oxygen's definitely a nonmetal, so that means hydrogen will have an oxidation state of +1. Now that we know hydrogen, we can use rule number 1 to solve for the oxidation state of oxygen, because we know that the sum of all the oxidation states have to add to our total charge, which for water has a total charge of 0. All right? And we can solve this because we know the oxidation state of hydrogen is +1. Equals 0. So if 2 plus the oxidation state of oxygen equals 0, that means the oxidation state of oxygen in this molecule must be -2. All right, what about, let's assign the oxidation states in lithium hydride. All right, again, we're going to need to use rule number 2. And since hydrogen is the only nonmetal, right, lithium's a metal, since hydrogen's the only nonmetal, its oxidation state is -1. That means that lithium's oxidation state must be +1. All right? Let's do one more example. What is the oxidation state of hydrogen in a molecule of H2? The answer is the oxidation state of hydrogen is 0. You're like, wait a minute. What about rule number 2? Remember, you only use rule number 2 if you can't use rule number 1. But rule number 1 says that the oxidation state of all elements must add to their total charge. Since we have a total charge of 0, that means that the oxidation state of hydrogen must be 0. So remember, as you learn these new rules, always go to rule number 1 first. And if that's enough to solve it, then that will get you your correct oxidation state. Rule number 3. Rule number 3. Main group metals. Main group metals have oxidation states equal to their normal ionic charges. All right. Oxidation states. The oxidation states of main group metals will be equal to their normal ionic charges. This allows us to assign oxidation states for molecules like the following. Let's assign the oxidation state for every element in magnesium sulfide. All right. So magnesium. So first, rule number one can't help us yet, right? Rule number one only helps if you have one unknown element left, right? So one doesn't help us yet. Two doesn't help us because we don't have any hydrogen. But three helps us because magnesium is a main group metal. So you find it on the periodic table, determine its normal ionic charge, and that will be its oxidation state. Since magnesium sulfide has no total charge, that means sulfide, or sulfur must have an oxidation state of -2, so that those two oxidation states together add to our total charge of 0. All right, what about, let's do this one. Let's do something a little more complicated. Calcium hydroxide. All right, now, rule number one can't help us yet, but rule number two can, right? Hydrogen is always +1 unless it's the only nonmetal. Is it the only nonmetal in this compound? The answer is no. Oxygen's a nonmetal. So we know that hydrogen will have a charge of +1. All right. Rule number three, main group metals will have oxidation states equal to their normal ionic charges. Calcium is a main group metal, so it will pick up a charge of +2. Now that we're down to one element where we don't know the oxidation state, now we can use rule number one because we know that calcium, the oxidation state of calcium, plus the oxidation state of both oxygens, plus the oxidation states of both hydrogens will add to our total charge, which is 0. We know that calcium is a +2. Oxygen, again, we don't know yet. I'm putting that little multiplied sign so you don't think I'm writing 20. +2 times +1 equals 0. So we have a +4 plus 2 times the oxidation state of oxygen is equal to 0. Now we subtract 4 from both sides and we get that 2 times the oxidation state of oxygen is equal to -4. And our final move, we divide both sides by 2 to find that oxygen's oxidation state in this compound is -2. Okay, so that is applying rule number 3. Now let's go to our fourth and final rule for oxidation states. Oh, no worries. Totally no worries. Okay, number 4. And this is our last stop. You only go here if you have no other options available. The most electronegative atom, or I should say the most electronegative atom's oxidation state, will equal its normal ionic charge. And just as a reminder, about electronegativity, which I'm sure you covered in your prereq class, but electronegativity increases as you move from left to right on the periodic table, and it increases as you move from the bottom to the top. So this is how electronegativity changes as you move across the periodic table. Ah, Angelina. Great observation. You totally can. So Angelina was asking, when you're doing polyatomic ions, can you do the polyatomic ions separately as far as adding oxidation states? And you can, but the thing you have to remember, so if you flash back to our previous example, oops, do this in black. So if you're going to do these separately, you totally can, but you have to remember the charge. So whenever you're dealing with an ionic compound, you can always assign the cation and anion separately. So if you do, then you're dealing with a calcium cation and a hydroxide anion. So it'd be H plus O equals total charge of -1, and it would be calcium is equal to total charge of +2. So you can totally do that, Angelina, but you've got to remember that you're not dealing, if you're dealing with the ions separately, they're not neutral. You have to remember what your total charge is for each one if you're going to get the correct answer. Totally valid way to do it. All right. Now, you are welcome. Okay, so now let's do a few examples where we apply this rule. All right. So, let's do H2SO4. All right. Rule number 2 instantly comes into play, right? Hydrogen is with 2 other nonmetals, so it's going to be +1. All right. Now, rule number 3 doesn't help us, so we have to go to rule number 4. All right. We've got to drop down and look at electronegativities. And when you bust out the periodic table, you can see that oxygen is here, right above sulfur, and we know the higher you are on the periodic table, the more electronegative you'll be, and so oxygen is more electronegative than sulfur, so oxygen will take its regular ionic charge, which is -2, and now we can solve for the oxidation state of sulfur because we know that the sum of all of our oxidation states must add to our total charge, which for sulfuric acid is 0. All right, so we have 2 times +1, oxidation state of hydrogen, plus sulfur plus 4 times the oxidation state of oxygen, which is -2. That is equal to 0. All right, so we have 2 plus sulfur minus 6. No, what am I saying? 4 times negative 2 is negative 8. Minus 8 equals 0. So we have sulfur minus 6 equals 0. So that means sulfur must have an oxidation state of positive 6. All right, question. Rule number 4 to sulfur. So we do apply rule number 4, but Cameron, great question. Okay, so Cameron's question is, why could you not apply rule number 4 to sulfur? Rule number 4 states that the most electronegative element picks up its regular ionic charge, and when you look at where oxygen lies on the periodic table relative to sulfur, oxygen's right here, sulfur's right beneath it, and so oxygen is more electronegative. And rule number 4 always applies to the more electronegative element. Isabel. It will not always equal 0. You have to look. The sum of the oxidation states will always equal the total charge on the species. So you always have to see, are we dealing with something that's charged? Are we dealing with something that's neutral? Because that is what will determine your oxidation state. Cameron, you are totally welcome. Let's take a look. Let's do 2 more examples here. All right. So, 2 more examples. Let's assign our oxidation states for, the polyatomic ion bicarbonate. You are welcome. Okay, so, and actually, Isabel, your question is pertinent to the example we're about to do right now. So, let's assign our oxidation states. Hydrogen here is a +1 because it's with other nonmetals. But we don't have any main group metals, so rule number 3 can't help us. We have to turn to the periodic table to see which element is more electronegative, and we're dealing with oxygen versus carbon. They're on the same row, they're on the same period, but oxygen is farther to the right, so oxygen will take its regular ionic charge, which is -2. All right. And so now we have enough information to determine the oxidation state of carbon, because we know that the oxidation state of hydrogen plus the oxidation state of carbon plus the oxidation state of all 3 oxygens must equal our total charge, which for this species is a -1. All right? So we have a +1 for the oxidation state of hydrogen plus carbon +3 times the oxidation state of oxygen is equal to -1. So we have carbon -5, right, is equal to -1, and now we have to add 5 to both sides of this equation to find our oxidation state of carbon. So carbon here has an oxidation state of +4. So those are our oxidation states. I'd like to do one final example before we move on. All right. So, one last example. Let's assign the oxidation states for every element in the polyatomic ion chlorite. All right, no hydrogen, no main group metals, so we jump straight to rule number 4. We need to know what is more electronegative, chlorine or oxygen. And when you look at their positions, oxygen is 1 row higher, but chlorine is 1 row further to the right. So what wins? So before we saw between 2 choices, oxygen and sulfur, oxygen's higher, pick that one. Between oxygen and carbon, oxygen's further to the right. So that makes it more electronegative. But what happens when you have one thing that's 1 higher, but the other thing is 1 further to the right? What wins that tie? And in the case of a tie, the tiebreaker goes to the higher element. All right, so oxygen wins the tiebreaker here because it is higher up on the periodic table. It is the more electronegative. Therefore, we give oxygen its regular ionic charge in this molecule. So oxygen takes an oxidation state of -2, and now we can find chlorine's oxidation state, because chlorine plus 2 times the oxidation state of oxygen is equal to our total charge, which is -1. So we have chlorine plus 2 times -2 is equal to -1. So we have chlorine minus 4 equals -1, and then we add 4 to both sides, and we find that chlorine has an oxidation state of +3. All right, so at this moment in time, you have seen enough to be able to handle any oxidation state I can throw at you. Now, let's apply this and actually solve a problem. So, for the following example, here's what I want you to do. Determine the element that is oxidized and the element that is reduced. In the following equation. A reaction between 8 molecules of hydroxide with 1 molecule of H2S and 4 molecules of chlorine, producing 1 molecule of sulfuric acid, 4 water molecules, and 8 chloride ions. All right. Now, this might seem a bit daunting. It might seem a bit overwhelming at first, but the way you solve any problem like this, anytime you're asked to determine the element that's oxidized or the element that is reduced, All you have to do is assign all the oxidation states, assign the oxidation state to every element in this reaction, and then look for what changes. All right, so step 1, assign your oxidation state. Step 2, determine which elements have changing oxidation states, and that will zero you in on who is gaining electrons and who is losing electrons, who is buying and who is selling. All right, and we're going to use the rules for assigning oxidation states to accomplish step 1. So let's do it. First, let's look at hydroxide. We know that hydrogen, rule number 2, because it's with another nonmetal, will have a charge of +1. So therefore, oxygen plus hydrogen will have to equal our total charge of -1. So oxygen plus the oxidation state of hydrogen, which is 1, there we go, is equal to -1. So oxygen will end up having an oxidation state of -2. All right, looking at hydrogen sulfide, all right, hydrogen's with another nonmetal, so rule number 2, it's going to be +1. We've got 2 H's, or +1. That means our sulfide must have a charge of -2. All right, for chlorine, its total charge is 0, and it's the only element present, so the oxidation state there must be 0. Looking at H2SO4, hydrogen is with other nonmetals, so it's +1. Oxygen and sulfur, we actually did this on the previous slide. Oxygen's more electronegative, so it's going to be have an oxidation state of -2. And so we're going to have 2, so we have 2 times the oxidation state of hydrogen, which is a +1, plus the oxidation state of sulfur, plus 4 times the oxidation state of oxygen is equal to our total charge, which is 0. So if sulfur plus 2 minus 8 equals 0, then sulfur is a +6. All right. There we go. Okay, looking at H2O, hydrogen is +1, it's with a nonmetal. Oxygen has to be a -2 because we have 2 +1s and our total charge is 0. Finally, chloride, our total charge is -1, so chlorine's oxidation state must equal that total charge. So here we have all of the oxidation states assigned. Next, to determine the element that's oxidized and the element that is reduced, we need to identify which oxidation states are changing. Kate, excellent question. Excellent question. So Kate asked, when you're assigning oxidation states, do you always ignore the stoichiometric coefficients? And the answer is yes. The stoichiometric coefficients tell you how many of that molecule are present, but the oxidation state of every element within a molecule will be the same no matter which molecule you're looking at. So you only look at the molecule in isolation of its stoichiometric coefficient. Great question. Okay. Now that we've assigned oxidation states, we have to look for oxidation states that are changing. All right, and one that jumps out to me right away is chlorine starts at 0 and ends at -1. That's a clear change, right? So you have to so we know that chlorine will be an element that's involved in the electron exchange. All right? Chlorine will be one element that's involved in the electron exchange. Where is the other one? The other one is sulfur. Sulfur starts at -2 and ends at a +6. All right? So if we look at sulfur, sulfur starts -2, ends at a +6. You have to ask yourself, has it gained or lost negative particles? And if you're starting negative and ending positive, you have lost. And Leo says, Gur, lose electrons, oxidation. So sulfur is oxidized. All right? Let's look at chlorine. Chlorine starts at 0. You're welcome. Starts at 0, ends at -1. So it has gained negative particles. It has gained electrons. Gur, right? Gain electrons, reduction. We say sulfur is reduced. Sorry, I said sulfur. Chlorine is reduced because it's gained electrons. Sulfur is oxidized because it has lost electrons. Now let me ask you a question. What reactant caused this reduction? What reactant did chlorine react with that caused chlorine to be reduced? All right. What caused the reduction? And the answer is H2S. All right? This is the molecule that reacted with chlorine, causing the reduction to happen. So because of this, we say that H2S is the reducing agent. All right? Because it is the reactant to the molecule that caused the reduction to happen. We could ask the same question of sulfur. We know sulfur is the element that got oxidized, but we could ask what reactant caused the oxidation? All right, what reactant caused the oxidation? And the answer is the reactant that reacts with H2S, causing it to be oxidized, is Cl2, the molecule Cl2. So we say that Cl2 is the oxidizing agent. All right, chlorine is the reducing agent. Sorry, chlorine is the oxidizing agent, H2S is the reducing agent. All right. Now, something that you may notice about the oxidizing agent and reducing agent. The oxidizing agent will always contain, so the oxidizing agent contains, oh my goodness, Photoshop's spazzing out a little bit. There we go. The oxidizing agent contains the reduced element and the reducing agent contains go. The reducing agent contains the oxidized element. All right. Okay. So, let's see. We got like 20 minutes. Here's what I'm going to do. I'm going to write a couple examples for you to try on your own. So for both of these, identify the oxidizing and reducing agents. I'm not going to do these right now for the sake of time. We're going to move forward and talk about how to balance redox reactions. But give these a try, and I'm more than happy to work them out in office hours. But for the following two chemical reactions, identify the oxidizing agent and reducing agent. And then for this reaction, I'm sorry, this is, whoa, there we go. This is a 4. All right. So you can take a stab at these two problems. If you want to see me work them, hit me up in office hours. But for now, in lecture, we're going to move on and talk about balancing redox reactions. Which you may hear that and think, wait, what? We know how to balance chemical equations. We've been doing that all semester, pretty much. Why are we talking about it here? Well, turns out that balancing redox reactions is not as straightforward as balancing other kinds of reactions. And the reason for this is for every reaction that we've done so far, our charges, the charges of those reactions have been balanced on either side, and they've started that way and they've ended that way. With redox reactions, they often won't start that way automatically, And so in addition to balancing our atoms, we also have to learn how to balance charges at the same time. So that's what adds the wrinkle here. Hang on one sec. We got a question. Amanda, great question. Amanda was asking if I'll be able to answer questions about Lab 2 and office hours tonight, and I absolutely will. So, as a reminder, tonight we have office hours from 7 to 10. Totally drop by, hang out. We can talk about. It's open office hours. There's no pre-programming. I'm there to talk about whatever you need help with. So hit me up, and I will help you out. All right, now. Balancing redox reactions. To balance a redox reaction, there's this method called the half reaction method. All right, and I'm going to teach it to you, and it may seem at first unnecessarily lengthy, especially because the first few examples that I'm going to give you might seem simple, and you might look at them and go, "I don't need the half reaction method to do that." Amanda, you're totally welcome. But don't let the first few examples kind of lull you into a false sense of security. You do need to learn how to do this because you'll be given more complex examples where you won't just be able to eyeball it and kind of figure it out. So I'm going to start easy with the easier problems, and then we're going to build complexity. All right, so hopefully by the time we get to the later examples, you'll be like, yes, I need the half reaction method. But we may not get to the more complex examples today. Those might have to wait till Wednesday. So don't be lulled into a false sense of security. All right, here's how the half reaction method works. You start by you split your reaction into two half reactions, all right? One half reaction has the redox reaction, the oxidation half reaction. The other half has the reduction half reaction. So you kind of split these into, here's the here's the oxidation, here's the reduction. Balance the two separately and then recombine them. That's the big idea. So you start by splitting them. Step number 1 for each is you need to balance your atoms first. You balance your atoms. Second, you balance your charges. Something to note, you balance your charges with electrons. We'll talk about how to do that in a moment. And then third, you have to balance your electrons. We'll talk about what that means. And then finally, you recombine the two half reactions that you split up in the first place once you've individually balanced your atoms, charges, and electrons. All right, now, what do I mean by any of this? You might be looking at that and going, that doesn't make any sense to me. Here's it in action, all right? I'm going to keep that there as the banner so that we'll kind of have that as a reference. But let's consider the reaction between solid chromium atoms and chlorine molecules to produce chromium ions and chloride ions. All right. Step number 1 in the half reaction method states that you have to split this into two half reactions. Basically, you take chromium. One half reaction will be the reaction with chromium. The second half reaction will be the reaction with chlorine, and you write these as two separate reactions. So we're just going to write chromium atoms going to chromium ions. Then we're going to write chlorine molecules going to chloride ions. All right, and these two we're going to deal with separately until we're ready to recombine them. All right, let's look. So that's the first step. That's how you split them. You've got your chromium half reaction and your chlorine half reaction. First, let's look at atoms. All right, our atoms oops, hang on 1 second. So from our atoms perspective, we have chromium on both sides of this half reaction, and we have one of each. So chromium's balanced. Let's look at chlorine. For our chlorine half reaction, we have 2 on the reactant side and only 1 on the product side, so we need to multiply chloride by 2. So now we have the same number of chlorine atoms on both sides of the half reaction. All right? So we've split, our atoms are balanced. Now we have to balance charges, and you can only balance charges with electrons. All right? Let's look at our charge. So at the start, for the chromium half reaction, we have 0 charges on the reactant side, and we have a charge of +3 on the product side. We have to make sure that our charges are balanced, meaning that the total charge on the reactant side equals the total charge on the product side. All right? So that's what we need to do. When you're balancing charges, you can only add electrons. All right? So you can either add electrons to the reactant side or the product side. For chromium, if we add an electron to the reactant side, that 0 is going to become a -1, right? We'll have a total charge of -1. It'll get further. So what we need to do is we need to add electrons to our product side so that our charges become equal. See, once you add 3 electrons to our product side, you've got a +3 charge coming from chromium, but now you have a -3 charge from your electrons, and +3 minus 3, 3 minus 3 is 0, and now the charges for both sides of this half reaction are equal. Let's look at the charges for our chlorine half reaction. So our charge on our reactant side is 0. Our charge on our product side is 2 times -1, right? Or -2. Now again, you can only add electrons to your half reaction. So if we need the charges on both sides of this half reaction to be equal, then we're going to need to add electrons to our reactant side, right? So we need to add 2 electrons here. Oops. To the reactant side. That way we have 0 plus a -2 is -2, and now the charges are balanced on both sides of our half reaction. All right, so we balanced our atoms, balanced our charges. Now, what does it mean to balance electrons? All right, what does it mean to balance electrons? Let's take a look. All right, so when it comes to balancing electrons, okay, in a redox reaction, as we can see, we have these 2 half reactions. When you're dealing with a redox reaction, you need to make sure that every electron produced by the oxidation half reaction is being consumed by the reduction half reaction, right? We know that in a redox reaction, you don't actually see the electrons changing hands, right? It's like a drug deal. So we need to make sure that there are no leftover electrons being produced by the oxidation reaction, that every electron produced in one is being consumed in the other, all right? Now, the way you do that is you have to ask yourself, okay, well, how many times does 2 go into 3? Well, not evenly in this instance. So what you have to do to balance your half reactions is we're going to multiply here our chromium half reaction by the number of electrons in our chlorine half reaction, and we're going to multiply our chlorine half reaction by the number of electrons in our chromium half reaction. When we do this, you'll notice that we get, on the chromium side, 2 chromium atoms produce 2 chromium 3 ions plus 6 electrons. And when we multiply our chlorine half reaction, you'll notice we get 6 electrons plus 3 molecules of chlorine, producing 6 chloride ions. And this is what we're talking about when we talk about balanced electrons. We're talking about one half reaction producing the same amount of electrons that the other half reaction consumes. And once those two are balanced, you're ready to recombine, all right? You're ready to bring these together in the final step of this problem. So I am going to rewrite what we had previously. We had 2 chromium atoms producing 2 chromium 3 ions plus 6 electrons. In one half reaction, the second half reaction had 6 electrons plus where was it? There we go. 3 chlorine molecules producing 6 chloride anions. We add these together. And when we add these together, we add everything on the product side together to make a new product side of the reaction. Everything on the reactant side gets crunched together. But one thing you'll notice is that we have 6 electrons on the reactant side, and we have 6 electrons on the product side. Whenever you have something on both the reactants and product side, they cancel, right? Just like with our spectator ions. So our 6 electrons on the reactant side of one half reaction cancel the 6 electrons on the product side of the other half reaction. And we get 2 chromium atoms plus 3 chlorine molecules producing 2 chromium 3 ions and 6 chloride ions. All right, and this is your balanced redox reaction. All right, now the redox reaction problem is lengthy. If you want to check checked. That's not a word. If you want to check to see if you did this correctly, all right, if your answer is correct, it's going to have two things have to check out. Your atoms have to be balanced. You have to have the same atom count on both sides. And you have to have the same total charge on both sides. All right. And you can see that you have 2 positive 3s and 6 negative 1s. So positive 6 plus negative 6 is 0 on the product side. Nothing's charged on the reactant side, so charge is balanced. And you can also see that both sides have 2 chromium atoms and 6 chlorine atoms. So that is how you check to see if your answer is correct. Once you come to the conclusion of the half reaction method. All right, now this reaction was as easy as these get. We're going to resume here on Wednesday. We're going to do more complex examples of using the half reaction method. One thing I want to say is historically for me in my classes, balancing redox reactions historically tends to be the lowest average on any problem that I give. This tends to be the thing that students struggle the most with. So this is something that you want to practice, all right? Because it's usually the hardest thing on the exam that it shows up on. So anyways, don't want to be scary, but just you want to give this a healthy amount of time. It's a very different type of problem. Many students find it challenging, so don't be too hard on yourself if you do find it hard or confusing, but give yourself enough time to practice so that you can master the situation. All right, that is it for lecture today. I'll catch you all, or some of you, hopefully, tonight in office hours, and the rest of you, I'll see you